Hi guys, it's Dr. Bay and here's Bugsy, and today we're going to go over synthetic strategies using enolates and amines, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Recall that when an aldehyde is treated with NaOH, an aldol reaction occurs and the product is a beta-hydroxyaldehyde or ketone. And if heat is added, then dehydration occurs to form an alpha-beta unsaturated carbonyl. Crossed aldol condensations can occur with two different carbonyls under the same conditions of NaOH and heat, and even intramolecular aldol condensations can occur where the two carbonyls are in the same molecule and a ring is formed, although this is only favorable if the product is either a 5 or 6-membered ring. Furthermore, a condensation is when two esters react with one another using NaOET as a base in the first step and H3O+ in the second step to form a beta-keto ester. Crossed Claisen condensations can occur when you have two different esters under the same conditions. And an intramolecular Claisen condensation can occur, which is called Dieckmann cyclization, but again, this is only favorable if the product forms either a 5 or 6-membered ring. And lastly, Stork enamine synthesis can be used to form a diketone from a ketone through an enamine intermediate. We have learned so many different reactions that form new carbon-carbon bonds. More specifically, there are three types of reactions that could form compounds with two functional groups: the aldol addition, the Claisen condensation, and Stork enamine synthesis all can form difunctionalized molecules. However, they do differ from each other in the positioning of each functional group. In an aldol addition, two aldehydes are added together to form a beta-hydroxyaldehyde where the carbonyl is at C1 and the hydroxyl group is at C3. In a Claisen condensation, two esters are added together to form a beta-keto ester where the ester carbonyl is at C1 and the ketone carbonyl is at C3. In Stork enamine synthesis, the diketone final product has a carbonyl at C1 and another carbonyl at C5. Both aldol addition and Claisen condensation form 1,3 difunctionalized molecules, whereas Stork enamine synthesis forms 1,5 difunctionalized molecules. So when you perform a synthesis problem, you should take note at the positions of each functional group because it will dictate what type of reaction should be performed. So let's do an example. Propose a synthesis of the following transformation. Notice that the target molecule contains both a carbonyl and a carboxylic acid group. Now let's take a look at their carbon positions. Notice that it is a 1,3 difunctionalized molecule, which narrows down our final reaction to either an aldol addition or a Claisen condensation. Between these two reactions, remember that the product of a Claisen condensation is always a beta-keto ester, and we can easily change the ester to a carboxylic acid through hydrolysis. So the final step of the reaction should be changing the beta-keto ester to a carboxylic acid using an acid like H3O+. That means that this molecule can be formed via a Claisen condensation between two esters. A Claisen condensation between an ester and 4 carbons can be performed using NaOET and H3O+ to form the following beta-keto ester. And lastly, we just have to determine how to form this ester from the starting alcohol that was originally given in the problem. Starting with the primary alcohol, we can use Jones to change it to a carboxylic acid, then use NaOET and H2SO4 to change it to an ester. So the final proposed synthesis would be first step Jones, Second step, H2SO4 and NaOET, followed by Claisen condensation using NaOET and H3O+, and an excess amount of H3O+ would push the ester to become a carboxylic acid.
Organic.